Have you ever wondered why some AI models are so good at making predictions, but impossible to trust? Like, how do we know they're not just picking up on random patterns in the data? That's the big challenge in machine learning, balancing power with transparency. Today, we're diving into a cool new approach called SHAP-guided regularization, a way to make AI models both smarter and easier to understand. Let's start with a crash course on SHAP. SHAP stands for SHapley Additive explanations, a method that quantifies the contribution of each feature to a model's prediction. Think of it as a detective for machine learning. It identifies which variables, like age, income, or blood pressure, are most influential in a model's decision. But here's the catch. SHAP is typically used after a model is trained, not during. This research flips that script. The team behind this work asked, what if we used SHAP not just to explain models, but to guide how they're built? Their answer is a framework that injects SHAP-based rules directly into the training process. Imagine giving the model a set of guidelines to prioritize features that matter most while ignoring noise. So how does it work? They added 2 key penalties to the model's training. The first is an entropy penalty. Picture this, you're solving a puzzle, but instead of focusing on the most critical pieces, you're spreading your attention too thin. The entropy penalty forces the model to zero in on a small set of critical features, like a detective narrowing down suspects. This creates sparse explanations, making the model's decisions easier to interpret. The second penalty addresses stability. Consider this, if you tweak a single data point, like changing a patient's blood pressure by a tiny bit, the model's explanation shouldn't flip from high risk to low risk. The stability penalty ensures feature importance stays consistent, even with minor data variations. It's like making sure your detective's conclusions don't change if they mishear a witness's name. The results? This approach didn't just make models more transparent, it actually improved their predictive power. By reducing overfitting to random patterns and focusing on the right features, models generalized better to new data. And because explanations are stable and sparse, you can trust what they're telling you. This isn't just a tweak for researchers, it's a game changer for real-world applications. Imagine a doctor using an AI to diagnose patients. With SHAP-guided regularization, the AI's decisions aren't a black box. They're clear, reliable, and rooted in the most relevant data. Same goes for finance, self-driving cars, or any high-stakes field where you can't afford to guess why a model is right or wrong. Now let's zoom in on a specific example. LightGBM, a fast and efficient machine learning model. LightGBM uses histogram-based learning, grouping continuous data into bins to speed up training. But even the best models can be black boxes. By adding SHAP-based rules, the model learns to focus on the most meaningful features, like a chef using only the freshest ingredients instead of throwing everything in a pot. In tests, this approach kept LightGBM's accuracy high, whether predicting house prices or diagnosing diseases. But here's the real win. The model became far more interpretable. SHAP entropy, a measure of how spread out feature importance is, dropped significantly. That means decisions are now focused on just a few key factors, not scattered across many. Visuals in the study show this clearly. Imagine 2 versions of the same model, one where feature importance is all over the place, and another where it's tightly concentrated on the most relevant factors. The SHAP-guided version is like a well-organized recipe, not a chaotic kitchen. And the best part? This improvement didn't come at the cost of speed or accuracy. In fact, in some cases, the model outperformed others like XGBoost and Random Forest. It's a rare win-win, faster, more accurate, and easier to trust. So why does this matter? In fields where transparency is critical, like medical diagnostics or financial risk assessment, being able to explain a model's choices isn't just helpful, it's essential. This research shows we don't have to choose between powerful AI and clear explanations. With tools like SHAP-guided regularization, the future of machine learning is both smart and understandable. Next time you hear about AI making life-changing decisions, remember, the tools to make those decisions transparent are evolving fast. Thanks for watching, stay curious, and let's keep exploring the fascinating world of AI.